All right, let's go ahead and get right into this mesh analysis example problem. I'm going to go ahead and draw my circuit here. Let's just say I've got, I don't need to put a voltage source there. I do that every time just because I'm so used to it. That's how most circuits are going to start out, with a source. But let's just go ahead and switch it up a little bit just to make sure you're on your toes with mesh analysis. Let's go ahead and put a resistor here, and then another source just like that. Make this one real tricky looking, and I'll put ground right here. And let's say that our goal for this example problem is to determine Vx, Vy, and Vz. This will be another really good one. Another good one where we learn quite a bit of stuff from this problem. Because I think that seeing different circuits and seeing how they're solved is really beneficial. So mesh analysis, right? First and foremost, let's go ahead and step one is define the loop currents for each loop. So let's go ahead and define our loop currents. I'll go ahead and define them the same way that I always do so that I can get that plus minus match across my resistor. I go ahead and note the rest of the plus minuses according to the way that the current's flowing. Again, it doesn't matter which way you define the currents. All that matters is that your pluses and minuses are consistent with the direction of current that you pick. Let's call this I1 and we'll call this I2. And let's throw some component values in here. Let's give this a 1 volt voltage source. Let's give this a 3 volt. And then let's just, for the simplicity of the math, make all of the resistors 1K resistors. And what I'm trying to do is find Vx, Vy, and Vz, okay? So I need to go ahead and write the KVL expression for each loop, okay? So my first loop will be the one on the left. I usually like to start with a voltage source just because it's super easy to write. I know that I'm going from left to right across this voltage source. I'm going up by 1 volt, so I'm going to write plus 1 volt. When I get to this middle resistor here, I am dropping from plus to minus, right? But I'm dropping by I1 plus I2, the sum of those two currents that are entering that resistor, multiplied by the resistance, which is 1K. All right, and then my last little element here is this resistor, and I am clearly dropping from plus to minus, and that is going to be I1 by itself times 1K, and I set this whole thing equal to 0. All right. The second equation is going to be the second loop, and I am going to start with my voltage source and go this way. In this case, I'm dropping. I'm going from a plus to a minus right across the battery, so I'm going to write minus 3 volts. Then again, I get to this resistor, I'm dropping, so I have to write minus I2 times 1K. And then I get to the third resistor, which is this middle one, and I am dropping I1 plus I2. Of course, it's times 1K, and I'll set that equal to 0. All right? So now we have two equations, we have two unknowns, and we can go ahead and do the algebra to either do elimination or we can do substitution. We can really just do whatever it is that we want to do here. I'm going to go ahead and use the fact that this term is present in both equations. And so I'll just solve the bottom equation real quickly for this expression. I1 plus I2 times 1K. And now I can go ahead and throw that into the first equation. Oh, that's not going to help me, actually. Let me undo that. That is not going to help me. Let's just solve the first equation, the top equation, for I1. How about that? So I'll just take these and do the algebra on the next slide because I don't want to run out of room here. So let's actually do something like this. I'll actually shrink this. And I'll shrink this one as well. So if there's more space, all right, and then I'll switch over to the smaller pen. All right, so I'm going to solve this first equation for I1. So I'm going to get 1 volt minus I1 plus I2 times 1K equals I1 times 1K. Then I'll go ahead and divide everything by 1K just to make it easier. So 1 volt by 1K would give me 1 milliamp. That would give me I1 plus I2 because the 1K would cancel and I'd be just left with I1. All right, so now I could say 1 milliamp minus I2 is equal to 2 times I1, because I'm going to take this minus I1 and add it over to the other side. And then I could divide by 2 on both sides, so I get half a milliamp minus 0.5 times I2 gives me I1, okay? So now I've got that expression for I1. I can plug it into this equation, and I would get minus 3 volts minus I2 times 1K minus, and then for I1, let me actually create a little bit more space for myself. I'm plugging in to I1 what I just found, which is 0.5 milliamps minus 0.5 I2. So I'm going to write 0.5 milliamps minus 0.5 I2 plus I2 times 1K gives me 0. Okay, let me go ahead and kind of just do a whole bunch of algebra here. I'm going to add the 3 volts over to the other side first. And 0.5 milliamps, and then I've got minus a half I2 plus I2. That just gives me plus a half I2. And then that's times 1K, and that whole thing's going to be equal to 3 volts because I added it over to the other side. This is super algebra heavy. It's very easy to make mistakes. So this is the reason why a lot of people don't like mesh analysis. But it is, it is very systematic. Let's divide both sides by 1K. So I get minus I2 here. Then I get minus 0.5 milliamps plus a half I2. And the 1K goes away. And then on this side, 3 volts divided by 1K gives me 3 milliamps. And so I'm pretty close to solving for I2 here. We've got a minus I2, a minus a half I2, a minus a half a milliamp, and a 3 milliamps. So I can combine like terms. I get this to be minus 1.5 I2 is equal to 3.5 milliamps. So I2 is going to be 3.5 milliamps divided by negative 1.5, or 3.5 divided by 1.5 gives me 2.33 milliamps for I2. Okay, so I just solved for I2, and now I can go ahead and plug that back in here, and I get negative 0.5 milliamps minus a half times negative 2.33 milliamps gives me I1, and so I1 multiplied by a half, and then I subtract 0.5, and I get that this I1 is going to be, oh, sorry, I needed to add a half, plus 0.5, that should give me, yep, 1.667 milliamps. Okay, so I got I1 and I got I2, and now I would be able to go back to the beginning of this problem and solve for my voltages. I'll go ahead and do that in the next video. This video probably got a little bit long with all that algebra.